Hi. So today I want to talk about some connections between the courses of Calc 3 and DiffEq. Um, I should mention that here I'm not intending to introduce for the first time any of the topics in this video. I'm assuming you've already seen these topics in Calc 3 and in DiffEq. And my goal here is just to show links between them that are maybe not apparent because the notation in the courses can be so different. But in many cases, we do exactly the same thing in DiffEq or as we do in Calc 3, or if not exactly the same, maybe just a minor slight tweak. But yeah, very, very, very close connections between the two courses. So I want to showcase some of that in this video. In particular, the first thing I'm going to start with before we talk about techniques or methods or anything like that, just objects. In DiffEq, a very common object that we look at in the plane is slope fields, right? So in DiffEq, often we use the idea of a slope field, right? So we have what is a slope field? It's the idea of taking the plane and we attach a slope, so a single numerical quantity to every point in the plane, right? So typically this is given by some differential equation in normal form is usually how you think of it, right? So you write it as dy dx equals some function, right? So let's say s of xy for slope, and then that function s xy lets you plot a slope at every point. And so you can think of it as an arrow if you want, of just a small arrow, or you can think of it as, sometimes people don't even put an arrow, sometimes they just put a little marking, like at each point, right? Just a little dash, but just sort of angled about the point. So sometimes people will put a little arrow, sometimes people don't even draw the arrow, they just draw a little dash that's tilted according to whatever numerical slope is given. As opposed to in Calc 3, right, you have a favorite object of Calc 3, at least in the later part of Calc 3, is vector field, the vector field. And vector fields are at least in the plane, you could do this in other dimensions, right? But here I want to focus on 2D. So vector fields are usually given as a function that assigns a 2D vector to every point in the plane. And this would be, so it would look like something like this: fxy equals p of xy, q of xy. And at every point in the plane, you could draw a vector, right? So now you have, again, a vector here, maybe a vector there. But here's the difference. These aren't just slopes. These aren't just scalar quantities that specify a slope attached to every point. Here, you can have some being tiny and some being huge, some being really tiny, some being really huge, right? Typically, when we draw vector fields, if you draw really big vectors all the time, they start crashing into each other and it becomes unreadable. So it's convention to shrink the magnitudes by a lot when we draw vector fields, but it carries more information than the slope field, right? So that's the key thing here. In the slope field, right, this is less, they're very similar objects, but the slope field has less information, right? Because it's just a scalar attached to each point, right? It's just a scalar quantity, just a single numerical quantity, right? It's a number that gives a slope, right? So there's less info on that side. There's less info stored in a slope field, as opposed to in a vector field. Here, there's more info stored in a vector field because you have a slope and right, which usually we say direction for a vector versus slope, but in the plane, it's the same thing. Slope and also a magnitude at each point, right? In DiffEq, we aren't attaching magnitudes to these slopes, only slopes, right? So given a slope field, there isn't a way to get the vector field corresponding to the slope field because there isn't enough information there, right? How would you know what magnitude to put at each point? But you can actually go the other way, right? Given a vector field, if you wanted to just forget about the magnitude, right, and go get a slope field, you could, right? And how could you get the slope of these vectors in the plane, right? So how can you, let me know, go this way. So what would be, if you wanted to construct a slope field from a vector field, what could you do? Well, what you could do is you could just say, do good old rise over run, right? Let the slope be what? Be Q over P, right? Just take the, think of the vectors that are being graphed here, right? P is giving you the run, and then Q is a formula that's giving you the rise, right? So if you do Q over P, that gives you a slope that corresponds to each vector, and you could then plot that as a slope field, right? So if you want to just forget about magnitude, by taking the ratio of the components of a vector field, you could, right? And you could turn a vector field into a slope field. But you can go the other way, right? Here, there isn't, there isn't a unique way to go from a slope field to a vector field, right? But point being, there is a way to associate these two objects with each other, right? It's just kind of a one-dimensional, one-directional correspondence. So it's not well defined in the other direction. All right, so there's a natural correspondence between those, the main objects of DiffEq and of Calc 3. Now, of course, we have objects in math, but we don't just sort of look at them and put them in museums, right? That we do things with them. We have algorithms and processes attached to these objects. What in this context, what thing do we do all the time with a slope field that is essentially the same as something that we do with a vector field? Well, here's what I want to do. I claim that very, very, very similar algorithms on the DiffEq side, when you solve, or here, let's back up before we even solve. Given a differential equation, and I'm going to say this is a differential equation given in differential form. And we'll talk very soon about why am I switching between differential form and normal form. So given a differential equation in differential form, which we write as p dx plus q dy equals 0. Right, so if you write your differential equation in differential form, this can be tested to see if it is what we call exact, right? This is something that you do in differential equations. And this, I claim, corresponds perfectly to the idea that in Calc 3, given a vector field, right, given a vector field F with components P and Q, let's test to see if it's conservative, right? So these are two things that we do in these courses. I claim that these are exactly the same method. Here they're pretty much identical. So we have, how do you test to see if a DE is exact? Well, the test for exactness is what? You look and you see, is the partial of Q with respect to X equal to the partial of P with respect to Y, right? You ask, are those the same, right? And now let's look. Green will be our color of wormholing between our universes here. What could you do to get over to a corresponding test to see if a vector field is conservative. Well, we'll take the test for exactness and just subtract the dp dy from both sides, right? And what do you get? You get that dq dx minus dp dy equals 0, which this is exactly the test for conservativity, right? This is curl. This is saying, is the curl of f equal to 0, right? So asking if a vector field is conservative and testing if the curl equals 0 is identical to the test for exactness, right? So these two correspond perfectly with each other, right? The vector field PQ is conservative if and only if the differential equation p dx plus q dy equals 0 is exact, right? They align perfectly. Now there is a slight difference between these two in terms of how you then proceed, right? If your vector field isn't conservative, well, then you just sort of stop there and say, okay, it wasn't conservative. It wasn't a conservative vector field. What's different with with differential equations is if it fails the test for exactness, well, now you can start multiplying both sides by integrating factors, trying to make it exact, right? You can't do that with a vector field. You've now broken the vector field. You're not broken, but it's not the original vector field anymore, right? Whereas with a differential equation, it's set equal to 0, right? So you can multiply both sides by any integrating factor. It's still 0 on the right-hand side. It's still in differential form on the left-hand side. And it's still equivalent to the original differential equation in terms of the solution set, because all you've done is multiply both sides by some quantity. So that's what's interesting. That's where there is a slight difference here, is you can multiply by integrating factors to get a non-exact differential equation to become exact. But you can't just take a vector field and multiply both components by something and then say, oh, now I know I've made it conservative. Well, yeah, but it's not the original vector field, right? So there's a slight difference in how you proceed, right? But the test itself, the test for conservativity, or sometimes people say irrotational, right, to see if it's an irrotational vector field or a conservative vector field, that's identical to the test for exactness. All right. Now from there, where do we go? How do you proceed? Well, once you know that a vector field is exact, sorry, a vector field is conservative, right, then what do? You find a potential for a conservative vector field, right? This is really why we care about being a vector field being conservative, because then we know we can find a potential, right? Over here, why do you care about a differential equation being exact? Well, it lets you solve it, right? It lets you solve the differential equation. And I'm going to stop one step short of fully saying solve the D, but I'm just going to say find a function f of xy such that the total differential of f df is the left-hand side of our differential equation, right? P dx q dy equals, well, let's just leave it there, right? Which is to say, another way to say that is we want partial f with respect to x to equal p, and partial f with respect to y to equal q, right? This is the this is the main thing that you have to do to solve a differential equation by exactness, right? Notice I didn't quite go as far as saying what the solution curves are, right? There's that one extra step at the end of solving by exactness, where then you say f of xy equals c, right? That does connect back to Calc 3, but that's the trickiest part of all of this. That's where we're not just changing notation, but there's some interesting geometry happening there. So that last step of f of xy equals c, we'll get to that in a bit. Now, what I want to show next is that the math here is identical. And now I'm going to actually introduce an example, because this is one of these processes, finding a potential or finding a big F, such a total differential is the left-hand side of your DEE. This is one of those things where I think that trying to describe the process in general is only confuses the topic, and instead just seeing how it goes in an example, I think is the best way to go. So, but also my coffee is really far off. Here, let me get my coffee. Okay, there we go. There we go. More than my stumpy arm away from me is too far. All right, so let's transition. Armed with that sip, let's look at an example, right? So let's look at an example of all of this stuff that I'm talking about here. So let's consider the vector field f of xy, which I'll say is equal to x minus y negative x, right? So this this is exact. Oh my God, I can't keep the language straight now. This is proving the point, right? That these two ideas are interchangeable. This is conservative. There we go. Conservative because what? The derivative, the curl of this, right? Curl of f would be what? It would be gradient cross x minus y negative x, right? Which is what? It's ddx ddy cross x minus y minus x, and then I have ddx applied to negative x is -1 minus ddy applied to x minus y is -1, so I get a double negative. So I get -1 plus 1 is 0. Great. So it is conservative, right? This now it from this I could then go and find a potential, right? So let's find a potential. And what would the potential be? The potential f of x, just to remind ourselves, what's the definition of a potential? It's f of x such that big F equals the vector field. Gradient of big F equals the vector field little f, right? So what do I want? In particular, we need two things to be true, right? We need equation 1, I need that df dx, that partial derivative, equals x minus y, the first component, and I need that df dy equals negative x is the second component, right? Now here I can integrate both of these equations, right? So here I'm going to integrate with respect to x, and then on the other one I'm going to integrate with respect to y, right? And when I do this on this first equation, this tells me that f of x has to be what? It has to look like x squared over 2 minus xy plus a constant of integration, right? But remember, we're dealing with partial derivatives here. This constant of integration could be any function of y, because look at the equation. It's df dx, partial f with respect to x. So I could put cosine of y there. I could put e to the y there. I could put any function at all of y, and it'll just vanish when I take the partial with respect to x. So that's why we don't have just a plus c, but plus c of y, right? It's a constant of integration that can be any function of y. Similarly, on this second equation, I can do an antiderivative with respect to y. So I get the antiderivative of negative x is negative xy plus, let's say, some constant of integration d. But this constant of integration can be any function of x because I'm doing a partial derivative with respect to y. Plus d of x would vanish when you do partial y, right? So now this is what I mean, what I said before about rather than looking at a general algorithm, just it's easier to just show in an example how you can figure out what the potential is. We need both of these equations to be true simultaneously, right? So you can look at it and kind of by inspection figure out what d of x has to be. Well, d of x means a function of only x. Well, the other equation shows you what d of x is. There's the term that involves only x squared over 2, right? Then I have c of y. Well, what is c of y? Now I look at the other equation and I say c of y is the term that involves only y. Oh, there aren't any. So, okay, so it's 0, right? So I don't need any function of y at all. So there we go, stitching them together. Now I know, see, now I know d of x equals x over 2, squared over 2, and c of y equals 0. So then, what's my potential? F of xy equals x squared over 2 minus xy, and that's it, right? You don't need anything. You don't need anything else. This function will have the right partial with respect to x and the right partial with respect to y, and you can check those, right? You can do those calculations. You can verify that the gradient of this function equals the original vector field, right? So there we go. We found a potential for that vector field. Now, how do you interpret this geometrically? The way you interpret this geometrically is what? Well, this. Well, sorry. Let's look at this in DiffEq land first, and then we'll look at the geometry that connects them. So, similarly, right? If let's say this. Similarly, if you had the dE, right, the differential equation, which was x minus y dx plus negative x dy equals 0. If you had this differential equation, right, you could say it is exact because what? Well, because partial x of negative x equals negative 1, and so does partial y of x minus y, right? So it passes the test for exactness. And then you could solve, right? Then you could, okay, let's find f of x, y with, I want the total differential to equal that left-hand side, right? So I want df dx equal to x minus y and df dy to equal minus x. And these are the same two equations that we started with up here. So I'm not going to show how you would solve that again. How you solve that would be identical. You would write out the two equations, integrate each one, find your plus c of y and find your plus d of x by looking at the other formula, and that's it, right? So you would do that same math, right? Same as above, and when the dust settles, you would get that f of xy equals that same function, x squared over 2 minus xy. All right, so that's an example of just the vector field, the potential, right? Now, what I want to show at last is this last step where when you solve, so let's return to talking in general as opposed to just in this specific example. In DiffEq, right, when you solve the differential equation, what do? You have an exact equation that looks like this: p dx plus q dy equals 0, right? By setting fxy equal to c, right? That's the very last step of solving an exact DE, is you set your function big F equal to c, and you say that's the general solution, right? And it's probably an implicit formula, right? But that's fine. It's you could maybe if the algebra is not too bad, you could solve for y to get an explicit. But that's what you do, right? This gives you the solution curves. This equation f of xy equals c, where f is partial f with respect to x is p, and partial f with respect to y is q, right? This is the last thing that you do when you solve an exact equation in DiffEq. What does this correspond to in Calc 3? This corresponds to, so here we're at a not obvious at all correspondence. This corresponds to the fact in Calc 3, this is something you prove in Calc 3, that the gradient of a surface is always perpendicular to the level curves of that surface, of that same surface. Right? This is something in Calc 3 that you actually use a lot, especially when you do Lagrange multipliers, right? When this is the whole method of Lagrange multipliers is based on this fact. So it says if you have, z equals 1, z equals 2, z equals 3, etc., right? And then you plot the, so say these are the level curves of a surface, and then you plot the gradient, right? If you plot the gradient as vectors, anywhere they might be all kinds of different magnitudes, right? But wherever you plot them, they'll always be perpendicular to the level curves. Right. Oh, and I should, let's see, -3, -2, -1. I'm going to do that because the gradient, what I was drawing there would have been negative gradient, right? The gradient always points in the direction of increase. So you need your level curves are increasing in the direction that your gradient goes. So this is not apparent at first, right? Why these are the same things, why the solutions to an exact equation being f of x y equals c is equivalent to this fact from Calc 3, that the gradient of the surface is always perpendicular to a level curve. So much so that I'll be honest, I probably taught both of these courses 5 times before I realized that these two ideas were the same idea, despite having like gone through both ideas what I thought was thoroughly in my own head. So here's after I read a combined 10, I don't know, 20 times that I've taught these courses, here's what that correspondence is that I can now present to you. The correspondence between these two ideas is it's a surprisingly simple bit of algebra, which I'm going to do over here. It's not a lot of work to see that they're equivalent. You just have to do that work. So here's what the work is. Plug in those partials for P and Q on that left-hand side, and now rewrite the differential equation in normal form. Right? Get it in normal form. So if you put it in normal form, what does it become? So it becomes, normal form is where you solve for the derivative, right? dy dx. So subtract over the x term, right? And then, so we get a negative sign, and then divide. So we get dy dx equals, right, divide the dx off, and we get dy dx equals negative df dx over df dy. Right. So this is our differential equation written in normal form. We took our differential equation that was in differential form, right, and then we rewrote it in normal form. Okay. Well, what is this saying? If you say this in words, this is saying that the solution curve to this, or I shouldn't even say the solution, solutions to this DE have slope equal to negative df dx over df dy. So this slope, if it's equal to negative df dx over df dy, what is it perpendicular to? It's perpendicular to, how do you do a perpendicular slope? Negative reciprocal, right? So do a negative reciprocal of this slope. it has to be perpendicular to df dy over df dx. It has to be perpendicular to that slope. Right? We're interpreting that number as the slope. Okay, so now think of way up here, I had this one-way correspondence between a vector field and a slope field, right? So one way that you can write down a vector field that would correspond to that slope field, if you want, is you could say this would be the slope. Now I'm crossing back over to the Calc 3 side here. This quantity would be the slope of the vectors in the vector field df dx, df dy. Right? That's the slope of the vectors in the vector field, df dx, df dy, because you would take the rise divided by the run to get the slope of those vectors. Oh, but we have a special name for this vector field. If you take a function f and then write its partial derivative with respect to x in the x component and the partial derivative with respect to y in the y component, we have a name for that. That's the gradient of f. Right? That's the gradient. So here's the thing. We need, what do we need? We need y of x, right? The solutions on this side. The solutions, which we call, y as a function of x. We need those solutions to have a slope that's perpendicular to negative df dx over df dy, right? Or sorry, equal to negative df dx over df dy, which is perpendicular to df dy over df dx, which is the slope of the vector field given by the gradient. So how do I get perpendicular to that? Well, that's this fact here, level curves. Level curves are perpendicular to the gradient, right? So that's how, right? That's exactly the last connection, right? So this is the slope of, the slope over here is the slope of the vectors in the gradient, right? So the level curves of f are perpendicular to this. And that's exactly what we're looking for. We want to be perpendicular to the gradient. That's what the level curves do. Therefore, what's that last step? So this is sort of both all at once, both sides talking, right? Thus, the solutions to df dx plus df dy equals 0. Those solutions are the level curves of f. And how do you write down level curves? Well, you take your surface and you set it equal to a constant, whatever constant you want, right? So that's, there we go. That's the and that's how you finish solving an exact differential equation, right? So that last step is really justified by this fact from Calc 3, right? Or you could say that they're equivalent facts if you want. So, so that's our last connection there between the subjects. I want to show now, just to finish out that example, right? The differential equation that we had. That differential equation was this one here, right? So let's grab this dE. Right, this is an exact differential equation. This has what as its solutions? It's f of xy equals c which in this case looks like what? We had f of xy. We found that up here was x squared over 2 minus xy. X squared over 2 minus xy equals c. All right, that's our, those are the solutions to our differential equation. Right? Just using this, again, using this fact from Calc 3. So you just rearrange the dE from differential form into an equation in normal form, right? And it just turns out that the slope normal form is slope equals something, right? But that's something just happens to be perpendicular to the slope of the gradient, and thus must be the level curves, right? So that's what's happening there. All right, great. So I hope this was a useful and or interesting connection between the two subjects. Yeah, thanks for watching.